Hey everybody, this is Corey from pythonfordatascience.org. Welcome to QuickPy. The topic today is correlation in Python. So we're going to be going over how to do correlation measure or tests using the built-in Pandas method and using Scipy stats. So before we get going, let's go over a high-level view of what a correlation is. So correlation is a statistical test of association between variables that is measured on a -1 to 1 scale. The closer the correlation value is to -1 or 1, the stronger the association, and the closer to 0, the weaker the level of association is. There is no absolute values of what's considered um, weak, average, or strong, but here, some general guidelines are um, an absolute R value, which is a correlation value of 0 to zero point 0.2 is considered weak. 0.3 to zero point 0.6 is moderate level correlation, and zero point 0.7 to 1 is a strong level of correlation. There are three pretty common types of correlation methods done, each with their own assumptions that need to be checked to make sure that the results can be trusted or considered valid. These three are the Pearson correlation, which is probably the most common, followed by spearmint rank correlation, and then there's also the Kendall's-Tau-B correlation. And like I mentioned, each of these methods have different assumptions that need to be checked to make sure the results are considered valid. So now that we got the high level over, let's get to doing how to do it, the correlation test in Python. So you can see here I got the data set loaded. The data set has to do with diamonds. The value here that is x is the length of the diamond, y is the width of the diamond, and z is the depth. We're not using those, I just wanted you to know what those were about. So we are planning on testing the level of correlation using the Pearson method. For the Pearson correlation method, there's a couple assumptions we have to make, check for. So we know our values are ratio or interval measurements, so we're good there. And this test doesn't use cases where there's missing values. So each variable has to have a value in there. If one variable has a data point but the other one does not, it gets dropped. That observation gets dropped from the method, so it reduces the number of observations used. But as you see here, we have pretty close to 54,000, so we're plenty fine. The ones that you need to really check the assumptions is if there's a linear relationship between the variables, so that when you plot in a scatter plot, it forms like straight-ish line or something like that, but it's not curved. Curved indicates, something might want to use a different test. And also if there's homoscedasticity of the data. Easy way to check that again is if you just do a scatter plot and the data, make sure the data points don't look for like a cone, form a cone shape. So if you don't know what homoscedasticity is, it's a measure of make sure that the variables have the same variance. And that's really what it is. So we can get accurate readings of the variance within the data. What is the variance? If you're to, it's a little beyond the scope of it, but just to get an idea, if you're to do a scatter plot and then put a regression line in there, it's how far the data point is from that regression line. It's using that distance between the data point and the regression line. So let's get to it. An easy way to check, like I said, the linear relationship and the homoscedasticity is just to use a scatter plot. We can use the Pandas' built-in scatter plot method. Don't have to do anything too fancy, like hopping over to Seaborn or anything like that. Let's just use this. So we enter in the two columns, the two variables you want, and we can run it. See here, we do have that linear relationship looking. It's not curved or anything like that. It seems to be going pretty straight. But we do have this, kind of looks like a shotgun explosion or a cone. So leading me to believe that we are violating the assumption of homoscedasticity, um, which means Pearson's method wouldn't be the best method to measure the correlation value between these two variables. A more stringent test to do is we can do the Levene's test of homogeneous variances. And this is very easy to do from using Scipy stats. We just do stats dot Levene and then the variables that we are interested in. I'm going to run it. We get our value, our test value, and then we get a p-value, which is significant. So we are definitely violating the homoscedasticity of variance. So that would mean that the Pearson method is not the best method used to calculate the correlation values. Instead, we should probably be using the Spearman rank method. And the reason that is Spearman rank is a non-parametric test, which means it does not make any assumptions about the distribution of the data. Remember, the Pearson made the assumption about linearity and homoscedasticity. Spearman rank does not care about that because behind the scenes it's using a different way to calculate it. It's ranking the values. So only thing it needs, Spearman rank needs, is that what's called a monotonic relationship between the variables, and that's just as one variable increases, so does the other, or it decreases, and we have that. So we are good with that one. First, let's go over how to do the correlation tests using the built-in Pandas method. So to do the Pandas way, we just call our first variable .corr, and then the second variable. We run it. And that right there is doing the Pearson method calculation for the correlation value. So we get a strong correlation between the two. But what we should be doing is the Spearman method, since we violated homoscedasticity. And in order to do this, all we have to do is pass Spearman into the method argument that is a part of the core method. And then we can run that. And we get a higher value, 0.96, which is even stronger. Makes sense, right? As the carat increases the diamond, the price is going to increase the diamond. One bad thing about using the Pandas method to calculate correlation values is you don't get the significance value, and we want that to know if it's actually significant or not. That's where the Scipy stats come in. It's just as easy to calculate the correlation values for both Spearman and Pearson using the Scipy stats method, but it gives us the actual significance level. So we just do stats dot Pearson, and then our values of it, our variables of interest. And you run it. So we get the same or very similar R value, and then we get the P value. It's not labeled, unfortunately, but the first value is your correlation value, and the second value is the P value. And then to do the Spearman, it's just stats.Spearman, and then the same columns or variables of interest. We run that. They decided to label this one, but not Pearson. It is what it is. So the first value we have is the correlation value, and then we have the p-value. So there's a strong level of correlation between carat and price, and it is significant. So that is how you do correlation using the Pandas method and the Scipy method. If you want to do this on multiple variables, you have to create a for loop, and you can just iterate through them, and you can get all the values for there. If you are interested in more of an advanced way to kind of do it, if you do go over to pythonfordatascience.org and go to the correlation page, there are some custom methods that are there with a code for you to use. And I'll just give you a quick demonstration of these real quick. Okay, I lost my mouse there. I found it though. So these functions were developed to do multiple to do calculate correlation values on multiple values. So I'm just going to show you how to do it with the Pearson, even though it can handle Spearman as well. So actually, let's do it with Spearman, since that's the one we're supposed to be using. So the name of the function is lys underscore core p-values, and then we enter in the data frame columns that we want to be calculated. Then to make this a list. Okay. Now L-wise, this is a list-wise. So when you're testing multiple values, before you run them, you need to decide if you want to use list-wise deletion or pairwise deletion. If you're unfamiliar with the difference between those, list-wise is also called case-wise deletion. What that is for every single variable that is in that's being run in the matrix, they all have to have the same number of completed cases. So if Carrot has 53,000 cases, Price has 500 cases completed, and Depth has 53,000, it's only going to use 500 cases because Price that's all it has completed. So that's the limiting factor. Pairwise, it uses a different n based off of the pairs that are being paired at that time. So Carrot and Price would have an n of 500. Price and Depth would have an n of 500, but Carrot and Depth would have a n of 53,000 since these ones have more cases completed, so it uses the full cases there. So you do need to make that decision going in. And pass. Okay, let me just run it. So you see here, it returns it with a correlation test conducted using list-wise deletion because that's what we decided, which is that function. It gives the total observations. So you know how many was calculated for there. Spearman rank correlation values, it gives it to you in a matrix, and the significant values, it gives it to you in a matrix. If you want to use pairwise deletion, this one is very similar named. And I'm just going to copy this because it's the same stuff. Oops. And you see here, it returns a little bit differently. Decided on this layout because the ends are going to be different, so it's just easier for you to see the ends. So you get the variables being compared, the value, the correlation value, the p-value, the number of observations, and then the method used, so a Spearman rank since that was decided. And that's everything. If there's anything, additions or questions, please feel free to comment. Hop over to python for datascience.org and let us know of a topic or any questions you have. Thank you.